Hello viewers, welcome. Now taking you through the story for A-level physics paper 2, and this video I'm going to go through the topic of interference of wave fronts, and this video is suitable for students in both senior 5 and senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline of this paper. So physics paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics. The second part is electrostatics and electricity, where 3 questions come from these topics. Then you also have waves, where 2 questions come from these topics, and magnetism and AC, where 3 questions come from these topics. So in this video, I'm going to go through the part of wave fronts and their properties. Wave motion and sound transmission was completed, and now we are going to wave fronts and their properties, and there are mainly 3 properties which we are interested in. So we're interested in interference, diffraction, and polarization. So in this video we are going to go through this property of interference. On this platform, we are interested in the calculations, but remember, a question of physics has a number of parts. It has a part of definition, part of explanation, description, and derivation, and also calculation. So in this platform, we only do the part of calculations, which is the worked examples in this book, but other parts of the notes are available in this book called Mastering A-level Physics Paper 2. So I encourage you to get yourself a copy, and if you need a copy, contact the author on any of these 2 contacts, so you can get a complete syllabus of the book of the notes you need in A-level. Then also a complete set of books for physics. There are 3. We have physics paper 1, physics paper 2, and the topical question bank. Principal math, there are also 3 books: math paper 1, math paper 2, and the topical question bank. Subsidiary math, it is only 1 book, and the rest are for O-level. So for any of the books, contact the author on those contacts. So now we shall start our topic of interference of wave fronts. So by definition, interference of a wave is the superposition of waves from coherent sources resulting in 2 alternate regions of maximum and minimum intensity. So I'm interested in the word maximum intensity and the word minimum intensity. So at maximum intensity, there is what we call bright fringes, and at minimum intensity there is what we call dark fringes. So the regions of maximum intensity result when the crest of one wave coincides with the crest of the other wave. I think at the beginning we saw what a crest is. So when the crest of 2 waves coincide is when we get a bright fringe or maximum intensity, and that is called constructive interference. Remember, here we are brief in the notes part, because what we want is to write what leads us to the calculation. So if you see the notes, they are very brief and shallow, but I encourage you to buy the books I've told you to buy, and you'll be sorted. So we have talked about maximum intensity. What about minimum intensity? Minimum intensity is when dark fringes are formed. So see us use this word bright fringes and dark fringes in this topic frequently. So it occurs when a crest of one wave coincides with a trough of the other wave, and that is what we call destructive interference. So destructive interference leads to dark fringes, and constructive interference leads to bright fringes. That's what you should remember. There are some terms which we need to know for us to go to the calculations. One is what we call a path difference of two waves or wavefronts. So path difference is the difference in the distances traveled by two wave trains from the secondary sources to a point of overlap. For example, if one wave starts from here and reaches here, another wave starts from here and reaches here, the difference is what we call basically the path difference. But remember, we are under interference, meaning the two waves have to interfere. Therefore, if one moves from here up to here, another one moves from here up to here, this is distance A to B. This is the point of interference. Then this is C to B, meaning that distance BC is longer than AB, meaning that therefore when I subtract the two, A minus AB, CB minus AB, I'll get what we call a path difference. So path difference is the difference in the distances traveled by two waves. You get this distance and also this distance, subtract them and you'll get the path difference you want. So you're going to derive this thing called path difference. So you consider two coherent sources A and B with a distance d between them such that they produce light of wavelength lambda, which overlaps on a screen placed at a distance capital D, as shown below. So we shall need an illustration. So you have, they said they want two coherent sources. This is source A and this is source B, separated by distance d. That is why you see here small d. And they said there is a screen which is placed d at distance capital D from the source. That is why you see here capital D from the source. And this is like the midpoint of the two slits. When you draw a straight line, it reaches at point O. So to help us to derive something, as we shall go on. So one source will move from A up to this point here, meaning that if another wave from source B overlaps with a wave from source A at the screen, they told us they overlap at the screen. That's why here you see an overlap here. So the distance from the center to P, we call it YN. We shall see what it means. But our aim is, so far, is the path difference. So the path difference will be BP, because BP is long, of course. So BP minus AP. That is what we call the path difference. And by geometry, we shall draw a line from the midpoint of the slits to the point of overlap, which is dotted as you can see it. It is not a wave, it is just going to help us to get the path difference. So by geometry, if you draw a perpendicular from here to drop it to at line BP at 90 degrees, it means that these two will be equal. From here to here is equal to from here to here. Therefore, the extra distance is Bn, and that extra distance is what we call the path difference, the difference between the two waves, distance traveled by the two waves. So how do we get this Bn is our interest. So path difference, like I told you, BP minus AP is equal to Bn, and Bn is d sine theta. By resolving, so if you come here, if you look at this triangle ABN, you realize that when the angle is here, the opposite is Bn, and the hypotenuse is d. Therefore, we shall use sine because sine is equal to opposite over hypotenuse. Opposite is bn and the hypotenuse is d. Therefore, when I make bn the subject, I'll come up with d sine theta. So that is where the d sine theta came from. Then from triangle MOP, if we go back to MOP, by geometry, this angle is the same as this angle. So tan theta will be equal to opposite, which is yn, over adjacent, which is capital D. Then we shall make an assumption that if capital D is much greater than small d, it means that theta is a small angle. And for small angles measured in radians, theta approximates to sine theta and also approximates to tan theta. So what does that mean? It means that if I want angular position, when they want angular position, they want the value of theta. So in the calculation, they can ask for angular position. Always remember that angular position is equal to yn over capital D. Then the path difference is d sine theta. But we're already seeing that this one, and this one are approximately the same. So d sine theta is the same as approximates to d tan theta. And we know that tan theta is yn over d. So I come and substitute for tan theta here to come up with this as the expression for path difference. It is important, it will help us in getting other terms. So path difference, so we have seen two words. We have seen angular position, which is yn over capital D. Remember, it is capital D. Don't confuse capital D with small d. Small d is the separation of the slits or of the sources of waves. And capital D is the distance from the slit to the screen. Okay. So I've seen path difference and angular position. Next, let's talk about this thing called interference. So interference, we already looked at it, the definition, but now we shall summarize and say it is a superposition of two coherent waves giving rise to bright and dark fringes. Remember, bright fringes occur as a result of constructive interference, while dark fringes occur as a result of destructive interference. So there's a condition that if the path difference is an integral multiple of a full wavelength, that is n lambda, where n is an integer, it implies that constructive interference has occurred, and as a result, bright fringes will be formed. So the condition for bright fringes to be formed after interference, it is when the path difference here is an integral multiple of a full wavelength. So now we are going to equate this to this to come up with a condition for a bright fringe to be formed. And when you equate the two, shall come up with this. So this is the condition for a bright fringe to be formed, because sometimes they can ask for this value of yn. Now what is yn? Yn is the distance of the nth bright fringe from the center. So they can ask the distance of the 5th bright fringe from the center. It means that where there is n, you put 5. They can ask them for the distance of the 10th bright fringe from the center. That means where there is n, you put 10, like that. But we also need the formula for a dark fringe. So for a dark fringe, the condition is that the path difference is an odd multiple of half the wavelength. So it is this. So we shall equate this to the path difference to come up with a condition for a dark fringe. And when you equate, we shall come up with this, where yn is now the distance of the nth dark fringe. Know the difference? This one, it was bright fringe when there is just n. When there is n minus a half, it is a dark fringe from the center. So when they talk about dark fringe, always remember to use this. When they talk about a bright fringe, always remember to use this. So that we shall go through some of the questions. So question 1 came from U.A.C.E 2004 paper 2 question 3b, and it says two coherent sources at distance s apart. So what we used as small d is now capital S. S apart produce light of wavelength lambda, which overlap at a point on a screen at distance capital D from the sources to form an interference pattern. If lambda, the wavelength is this, S is this separation of the slits, and capital D is this, the distance from the slit to the screen, find the angular position of the first dark fringe on the screen. So for dark fringes to be formed, this is the condition. Therefore, the first dark fringe, it means n is 1. So I'll come and put 1 to get y1. So y1, where there is n, you put 1. We know wavelength, we know capital D. What we use as small d is now capital S, which is that, to come up with this as this position or the distance of the first dark fringe from the center. Therefore, angular position will be, remember angular position is yn over capital D. So for the first dark fringe, it means y1 over capital D. And y1 we have got it, and capital D we have it. That will be the angular position in radians, or you can convert to degrees. Then question 2 came from U.A.C.E 2002 paper 2 question 3c, and it says, in Young's double slit experiment, double slit are the two slits you saw. Remember, you saw the A and the B. That's what we call a double slit. So this word shouldn't confuse you. So in Young's double slit experiment, the 8th bright fringe, okay, is formed 5 millimeters away from the center of the fringe system. So this is 8th, meaning this is the value of y8. When the wavelength of light is used, when the wavelength of light used is this, so this is the value of lambda. Calculate the separation of two slits, that means the value of small d. If the distance from the slits, okay, so the repetition, this we cancel it, to the screen is 80 centimeters, this is the value of capital D. So shall come and first of all interpret what is given. This is y8, convert to meters. Then wavelength, it is that, and capital D is that. And they have talked about a bright fringe, meaning the formula I'm going to quote is the formula for a bright fringe to be formed. So for bright fringes, we have this formula, but our interest is the 8th bright fringe. That is why we are putting here 8. Where there is n, you put 8 to come up with that. And in the question, they want the value of d, so make d the subject to come up with this. Or that you substitute, 8 is here, capital D is here, because you have to convert from centimeters to meters. Then wavelength and y8 to give you this as the value of d which they wanted, separation of the slits. Then question 3 came from U.A.C.E 2015 paper 2 question 4c, and it says, in a Young's double slit experiment, 21 bright fringes occupy a distance of 3.6 millimeters, occupying a distance of 3.6 millimeters, were visible on the screen. Okay. The distance of the screen from the double slit is 29 centimeters. and the wavelength of the light used was this. Calculate the separation of the slits. Still here they want the value of small d. So you come and interpret the question. 1n is 21 and yn or y21 is 3.6 millimeters. Convert to meters. Then the wavelength is that, and the distance of the slits from the screen is 29 centimeters. Convert to meters. So now that you have interpreted the question, we shall come and say for bright fringes, this is the formula we have, but n is 21, so substitute where there is n, you put 21 and then make small d the subject. So 21 is here, capital D, wavelength, and y21 to give you this as the answer. And that's what they wanted. So now we shall go to question 4, which came from UNEB 1996 part 2, question 4C, and it says, in Young's experiment, an interference pattern in which the 10th bright fringe was 3.4 centimeters from the center of the pattern was obtained. The distance between the slits and the screen is 2 meters, while the screen separation was 0.34. Find the wavelength of the light source. So we have n was 10 because of the word 10th. So we have now y10 as 3.4 centimeters. And capital D is 2. Therefore here it was not screen, it was slit. So you edit this and put there the word slit. Slit separation was that. Therefore for bright fringe we have this formula. N is 10 here and here, and they want the wavelength, so make wavelength the subject and substitute y10 d, small d, 10 is here, capital D is here, to come up with this as the wavelength they wanted. So edit this and put there the word slit. Question 5 came from UNEB 2019 paper 2, question 3C, and it says, in an experiment to determine the wavelength of light using Young's method, 2 slits at a separation of this were used. When the screen was placed 18 centimeters from the slits, 30 bright fringes occupy a distance of 2.5 millimeters were obtained. Find the wavelength of light used. So you shall first interpret that this 1.2 millimeters is small d. Then the capital D is this 18 centimeters. Then n is 30. Therefore y30 is 2.5 millimeters. And so this one you ignore it. So for bright fringes we have this, but our interest is 30, so we shall put 30 where there is n, here and here. And they want the wavelength, so make it the subject. And substitute y30, small d, 30 is here, and capital D, to come up with this as the wavelength they wanted. So this one, just ignore it, it was a stray value. So we've looked at fringes or interference, and we looked at dark and bright fringes. But they can also ask you for the separation of fringes. So fringe separation is the distance between any 2 consecutive bright fringes or consecutive dark fringes. So you can put a bright fringe here and a bright fringe here. That will be the separation between the 2. Or a dark fringe and a dark fringe, and the separation will be, and the distance between the 2 is what we call a fringe separation. So it will either be between 2 bright fringes or between 2 dark fringes. That is what we call the fringe separation. So for the nth bright fringe, we have this, we already know that. That means that for the next bright fringe, it will be n plus 1. This was n, this is now n plus 1. Therefore, the separation will be got by subtracting the 2. And when I subtract the 2, I'll come up with this minus this. Open brackets here, I'll split the numerator to give you n lambda d here plus lambda d there. Then minus this. So realize that this and this can cancel to remain with only this. And that's the formula for fringe separation. Any two consecutive fringes. If they specify, then they can set different distance between the 8th and 4th bright fringe. It is okay. But when they just say fringe separation, just know that they have to be consecutive fringes. So that's the formula we have now seen. So question 1 came from U.A.C.E 1998 paper 2 question 3c, and it says monochromatic light of wavelength this is incident on two slits of separation this. Okay, calculate the fringe separation on a screen placed 1.5 meters from the slits. So still first is to interpret. Wavelength is there, small d is there, and capital D is there. Then shall come and say fringe separation is given by this formula, so substitute capital D, wavelength, and small d to come up with the separation they want. Then question 2 came from U.A.C.E 2001 paper 2 question 4c, and it says two slits 0.5 millimeters apart are placed at a distance of 1 meter from the screen. The slits are illuminated by light of wavelength 550 nanometer. This is nm, nanometer. Calculate the distance between the 4th and 2nd bright fringes of the interference pattern. That means they want the distance between y4 and y2. So interpret first, small d is that, capital D is that, and wavelength is that. So for bright fringes, this is what we have. Therefore, the distance between the 4th and 2nd bright fringe will be given by y4 minus y2, where y4 is this, y2 is this, to come up with this. So come and substitute for capital D, wavelength, and small d to come up with this as they wanted. Then question 3 came from U.A.C.E of 2014 paper 2 question 4b, and it says in Young's double slit experiment, two slits are 0.5 millimeters apart, and the interference is observed on the screen at a distance of 100 centimeters from the slits. It is found that the 9th bright fringe is at a distance of 8.84 centimeters from the 2nd dark fringe. Now here they've talked about a bright fringe, and here they've talked about a dark fringe. You should take note of that. From the center of the fringe pattern, find the wavelength used. So here you need to be aware of the formula for a bright fringe and the one for a dark fringe. So small d is here and capital D is here. And the distance, this is the bright fringe, this is the dark fringe, the distance between the two is that. So for a bright fringe, yn is this, imply that y9 will be given by that formula. Okay. What about for a dark fringe? For a dark fringe, yn is given by that, therefore y2 will be given by this formula. Therefore I'm going to subtract the 2. When I get this minus this, I'll be able to be equate it to this, which was given. So I'll come and substitute for yn and y2. Simplify and then substitute. Capital D is here, small d is here, then I can make lambda the subject. And that's what they wanted. So we have been looking at interference in Young's double slit experiment, but now we shall look at interference in an air-wedge experiment. So that is formation. We shall start with formation of interference fringes. Fringes are the dark and bright fringes. Remember we said dark fringes are due to destructive interference, while bright fringes are due to constructive interference. So what happens for the case of for an air wedge? So a very thin wedge of air film can be formed by placing a thin piece of foil between two microscope slides at one end and with the other slides in contact. So one end will be in contact and the other end will be separated by a metal foil, as you have seen the illustration. So you have a lower glass slide and this upper glass slide. So one end is in contact at an angle theta, then the other side is separated by a metal foil. It should be thin. And this D is what we call the thickness of the metal foil. Okay. And in between is what we call the air wedge. So we shall label this part A and this one part B for some derivations, which shall do. Okay. Then they said monochromatic light is directed to a slanting glass plate. So we shall need a glass plate which is slanting. Then you shall need monochromatic light incident on it. So the light is reflected almost normally to the glass slide. So from here it will be reflected to meet the glass slide. Let's do that. Okay. Then the incident light is partly reflected by the lower surface P of the top slide and partly transmitted to the lower slide. So here one will be reflected, another one will be transmitted to this lower slide. Let's do that. So one, there is that will be the reflected part and to be observed by an observer at that position. Another partly will be transmitted to the lower slide at point 2. So the transmitted light is reflected by the top surface 2 of the lower slide. So here it was the lower surface of the top slide, but here it will be the top surface of the lower slide. So there will be reflection to meet the observer still. So this will be the separation of this from here, T as T, and realize that now the observer receives 2 waves. So the 2 waves are coherent and so interfere to produce alternate dark and white fringes parallel to the line of intersection of the slides. So here we have drawn when you are viewing the slides from this side. But when you view it from this side, you will see something like this. So the interference will be parallel, the fringes will be parallel to that line of intersection. Now the path difference for a dark band to be formed at the edge B is given by this. That 2D is now the path difference. It will be equal to the integral multiple of yn. You realize that in the previous one it was not. This was the formation of a bright fringe, but now here is for a dark fringe. Why? Because of that phase change. There's a phase change here, but that will be seen more in the notes. Here we're interested in coming up with a formula which will be used in the calculation. So we read that in the notes of the book I've told you to buy, but what you need to know is that for a dark fringe, it is now 2D equal to n lambda, where n is the number of the dark fringes from edge A to edge B, and d is the thickness of the metal foil. Therefore, by counting n, the thickness of the metal foil can be found. Then the path difference for a bright fringe to be formed is given by this. So it is now the opposite. In Young's double-slit experiment, this was the condition for a bright fringe to be formed, and this was the condition for a dark fringe to be formed. But now in an air field, in an air wedge, it is now the reverse. This is the condition for a dark fringe, and this is the condition for a bright fringe. So you should know those two differences. But more of this explanation why they interchange can be got from the book. So derivation of the wedge angle and fringe separation. Now we are going to derive. So what we have been doing was just a simple introduction, simple notes for what an air wedge is. But our interest is the formula which will take us to the calculation. That is why the explanation is a little shallow. So complete explanations will be got from the book. So we are going to extract out something from the diagram. We shall extract out similarly a triangle. This is one triangle, and this is also another triangle. So this will be the point where a fringe is formed. That is yn, distance from the center to the point where a fringe is formed. Here it can be a dark fringe or a bright fringe. And this L is the distance from here up to here. And this is the thickness of the metal foil. This is the distance from the top slide to the lower slide. So from the above diagram, tan L, by similarity, tan L can be got by this using the big triangle, or can be got by this using the small triangle. So for the small triangle, T will be equal to yn tan theta. For nth dark fringe at P, when an nth dark fringe is seen, we shall come up with this. It means it will be this. So when it is at this point, you have to get the distance from here up to the lower slide. That is what you use. It is twice because at first one came here, another one went up. So this is twice movement from here to the lower slide, then from the lower slide to this. That will be the path difference to T is equal to n lambda. But T is equal to this. So come and substitute to come up with that. Then when I make yn the subject, I'll come up with that. Also, we know that tan theta is equal to this. Therefore, I'll come and substitute and get this. So these are the two formulas which can be used to get yn in an air wedge for a dark fringe. So for the next dark fringe, we have that, meaning I can easily get the fringe separation. So fringe separation will be given by that formula, and to be equal to lambda over 2 tan theta. But we already know that tan theta is d over L, so I can either use this formula or use this for fringe separation. So we have dealt with dark fringes. If they ask for a bright fringe, the difference will be here. If they had asked for a bright fringe, the difference will be on this n. Instead of n, we put n minus a half, but the rest will be the same. Okay, so with that we shall go through these questions. Question 1 came from U.A.C.E of November 1998, paper 2, question 4C, and it says 2 glass plates 12 centimeters long are in contact at one edge and separated at the other edge by a piece of metal foil which is this centimeters thick. When the plates are illuminated normally as shown below by light of wavelength this, a system of fringes are formed. Okay, find Roman 1 the separation of the fringes, and Roman 2 the number of dark fringes formed. So Roman 1, we know that capital L is 12 centimeters, small d is 2.5 exponent negative 3 centimeters, convert to meters. Then wavelength is nanometer, convert to meters. Then for fringe separation, we saw that it's given by this formula, so we shall come and substitute for wavelength, capital L, and small d to come up with this as the fringe separation. Then for Roman 2, they ask for the number of dark fringes formed. So here, assuming that a dark fringe is formed at the thickest edge of the wedge, it implies that 2d is equal to n lambda. If it was a bright fringe formed at the thickest end, instead of n we would have put n minus a half. But now because we are using dark fringe, we shall put just n. Then you make n the subject to come up with this as the number of dark fringes. Then question 2 came from U.A.C.E of 2008, part 2, question 4C, and it says 2 glass slides in contact at one end are separated by a sheet of paper 15 centimeters from the line of contact to form an air wedge. When the air wedge is illuminated normally by light of wavelength this, interference fringes of separation 1.8 millimeters are formed in the reflection. Find the thickness of the paper. So you first interpret capital L is 15 centimeters, wavelength is that, and the separation is 1.8, fringe separation. Then you quote the formula for fringe separation and make small d the subject. So substitute lambda, capital L, and fringe separation to give you this as the value of d, which is the thickness of the paper. Then question 3 came from U.A.C.E of 1997, paper 2, question 3C, and it says 2 glass slides in contact at one end are separated by a metal foil 12.5 centimeters from the line of contact to form an air wedge. When the air wedge is illuminated normally by light of wavelength this, interference fringes of separation this are found in reflection. Find the thickness of the metal foil. So still the same procedure. Capital L is that, lambda is that, separation is that, Therefore, quote the formula for fringe separation and make D the subject. After that, you substitute for lambda, capital L, and separation to come up with this as the answer. Then question 4 came from U.A.C.E 2017 paper 2 question 4C, and it says an air wedge is formed by placing two slides of length 5 centimeters in contact at one end and a wire at the other end as shown in the figure. When the slides are illuminated with light of wavelength this, 10 dark fringes are observed to occupy a distance of 2.5 millimeters. Determine the diameter of the wire. So interpreting, capital L is this, N is that, Y10 is that, and lambda is that. Therefore, for the nth dark fringe, you will come up with this, the formula for Yn. N is 10, so put 10 where there is N. Therefore, D will be given by this, so substitute, lambda is that. So what we have done, here we divided 2 divided by 10 will remain with 5. That is where this 5 is coming from. So lambda is this, capital L, and Y10 to come up with this as the thickness of the metal foil. Question 5 came from U.A.C.E 2015 paper 2 question 4B, and it says 2 glass slides are separated by a thin wire to form an air wedge. When the wedge is illuminated normally by light of wavelength this, a total of 20 fringes occupying a distance of 15 millimeters are obtained. Calculate the angle of the wedge. So shall I interpret the question? Lambda is that, N is 20, Y20 is that. Therefore, the nth dark fringe we have this formula, but N is 20, so substitute for 20 where there is N. They want the value of theta, so we make tan theta the subject. Then you will come and substitute for lambda and for Y10. After that, you make theta the subject by getting arctan, and that will be the angle they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on diffraction and polarization of wavefronts. So if you're not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.